In this video, we'd like to do a little overview of the kind of topics that are covered in a first course in differential equation. So let's begin. So the reason we want to do this is because when you go into a first course differential equation, it can be a little bit foreboding that you see all of these different techniques of solving differential equations, and you wonder, where is all of this going and why are we doing it, and so forth. So by having this kind of perspective that we hope to give here today, we hope that maybe going into the study of differential equations may be more easily appreciated, or the reason we're doing it and why we're doing it. So let's look at a summary and overview of the course in general. So the first question we want to ask was why, and what is the why of differential equations? So why do we need it? We need it because quite often in the analysis of phenomena, it's find it easier to study how some quantity of interest is changing rather than knowing what the quantity itself is doing as a function, let's say, of time or what have you. So here's an example. Suppose we find that the number of cancer cells are changing as a function of time, because that's what we can measure. And we find that it's changing in proportion to the number of cancer cells that are there at that particular time. From that, we can then solve that differential equation to find what is the n of t that makes that happen. And it turns out it's an exponential function, and it gives us the answer that we are seeking. So there's an example of where we would want to use it, and we'll get into a couple more in a few minutes. So what are we talking about then is, if we're given an equation that contains derivatives, find a functional relationship of some desired quantity that's present in there. So let's look at two motivational examples. One is, how does the number of infected people of a prevalent disease change with time? And two, what is the vaccine coverage we needed to eliminate a conflict? So let's look at the first problem. So it seems reasonable to say that the rate of change of the number sick is going to be proportional to the product of the number of sick now, an n of t number, and the number yet to get sick, c minus n, where the c is the susceptible people who could get this sickness, this disease. So we can write that dn dt is the product of three things: the proportional constant, the number that are sick now, the number sick now, right? And the number yet to get sick. So this is number sick now. Next one is the number of yet to get sick. Yet to get sick. And we can take and notice that this derivative is always going to be a positive number, with each one of the three terms themselves positive. So n is an increasing function, which doesn't surprise us. And further, without doing any more math, if we were to speculate on what this n of t looks like, we would say, well, it begins at some n0. At time 0, we have some number of people sick with it. And it's going to slowly increase to begin with, and then start to rapidly increase until it gets to a point that so many people are already sick, it's going to have to turn around. And if we have to guess, where does this turnaround point, or what we call the inflection point, where it goes from concave up to concave down, we would think it would be about at half the total number of people that could get sick. And sure enough, when you go through the math and solve this equation, right? So solving, and we learn how to do that in this class, in the first class in differential equation, we find that this is the answer we get, where the R number now is a normalized constant, is the product of the K number, the proportionality constant, and the number who could get sick. So this is a quantity, it's the percent change in the rate of infected people per unit of time. And it's going to be a positive number, right? And we can also ask, at what time does it get to the point where we have half the people are infected and we have to start to turn around? Because that's an important point, because then we can start to cut back on the number of health services. So you can see that given this information of the derivative, we can then use it to find the actual underlying function. So this would be our a result that we get from understanding how to solve some simple differential equation. And the next topic says, what is the vaccine coverage needed to eliminate a prevalent disease? So under certain conditions, a model for the vaccine coverage satisfies the following system of differential equation. That is, we start out in saying that the rate of change in those who are not vaccinated as a function of time is going to be given by a differential equation, which would be, turns out to be 1 minus 2p n of t, the number who are vaccinated that are sick, plus another term from the number that are vaccinated and also sick. The number that are vaccinated that are sick. That are also infected. And we get another differential equation relating to the vaccinated people, having the two terms, but now having a different constant in front of them, plus 2p minus 3 v of t. And the p number in all cases is the p is fraction of people vaccinated. That's a number that can go from 0 to 1. Nobody vaccinated to everybody vaccinated. So what we have here now, as opposed to what we had in a previous example, is not a single differential equation, but we have a system. Of first order, and again, we'll explain what first order means as we get in a little bit more, and linear system of ordinary differential equation. And we get into all these terms in a minute. And in this course, the details of solving these type of system of equations is provided. And so we find, using that procedure, which we'll be learning, that we can write the two terms that we need, the n and the v, as a vector that contains a constant that's a function of the number 6 times 0 that are not vaccinated, the number of 6 times 0 that are vaccinated, and this p number of the number of people that are proportion of the people that are vaccinated. And then my factor here, which is only dependent upon that p number, for one of the components, and exactly 1 for the other. And then multiplied by, so this term, these are all constant terms. They do not change with time. Do not change with time. And then a factor that does change with time. and it's e to the 2 times the square root of 1 minus p minus 1t, plus another term, which has another constant that's also of the same flavor, p0 and p, and another vector, 1 over p times the square root of 1 minus p plus p minus 1. And again, 1 down here. And again, this term is also not a function of time. And then a term that does change with time in a different way, but also a function of just that p number. Right? So we get all of that from being able to solve these differential equations. And this thing provides a lot of information. If you look at what this number is, it turns out it's always less than 0 for all p between 0 and 1, which is of interest to that domain. So this is going to be always decreasing. So the second term is always decreasing. Therefore, the second term always decreasing as time goes on. The first term, however, over here is not. It's less than 0 only if p is greater than 3/4. It's equal to 0 when p is equal to 3/4 and is less than 0, or 75% of the vaccinated. So then if we ask, what is the limit as t goes to infinity of the n of t over v of t, we find that it'll go to 0 if the p is greater than 3/4. So then at that point, it gets eliminated. So we could graph this stuff and say what's happening is that when we are at a p of less than 3/4, then as we look at the number of people who are not vaccinated and the number of people who are vaccinated that are getting sick, we'll find that regardless of where we start, wherever is our N0, V0 number, it'll take off. We start over here, it takes off. No matter where we start, it takes off. It's gone. If, on the other hand, we have a P of exactly 3/4, then we find that, again, regardless of where we start, N0, V0, we'll end up on that line down the middle, right? So we start up here, we'll come down here, and so on and so forth. No matter where we start, it's going to come down to that line. And further, we now take the third case where it's now greater than 3/4. We will see a different story, and a nice story, that now it's good, regardless of where we start, N0, V0, that is going to do something, but eventually get down to 0, right? Eventually get down to 0. We start up here, we go down and end up at 0. And this is what we're showing over here, where we put in some color coding. And the color coding comes in from the material we learned in calculus. In the calculus 1 and 2, we learned that a continuous function has basically 4 basic shapes: increasing in concave up, increasing in concave down, decreasing in concave up, decreasing in concave down. So the 4 basic shape, and gives you the 4 basic colors, and depending on the situation you get that. So here's a situation where it's uncontrolled. Here is where it's stabilized, and here's where it's concentrated. So that's the that's the thing. So you can see that we're talking about material here that's very, very essential. And even though we took these two examples, motivational example is from the medical field, really applies in engineering, of course, in biology, in all kinds of areas. There's really no limit to it. This basic differential equation, for example, is given a name. It's called the logistic growth equation, which comes up in a number of different applications. All right, and we can get a system of differential equations for a number of different applications, of which we only did one here. Okay, so that's hopefully motivates us to then say, okay, let's look at see what we're going to talk about. Now, what we're going to talk about then is the different types of differential equations, the ordinary differential equation or the partial differential equation. An ordinary differential equation only has derivatives of one or more unknown functions, like we had there, the unknown function being the number who are infected and are vaccinated, and the number who are vaccinated and not vaccinated. As a function of a simple independent variable, we took the independent variable here as time. And I could have partial differential equations where I have partial derivatives, and that is a topic beyond this first course in differential equation. And then we can characterize that with linear or not linear. You can appreciate that with linear, we can see a whole lot more things about it. And we'll be covering that in depth in this class a little bit. And then we can talk about a system of differential equations. We gave that one example. The second example was of that flavor of system. What can we say about that? So the topics then we plan to cover is to first start out by characterizing the differential equation that we summarize over there, looking at how we can solve first order differential equation like we did in example 1. And then look at the general tree of sorting an nth order, not just first degree, but second degree or third degree or more. We look at if I have a homogeneous equation, it's equals 0, it doesn't have any forcing function outside. How can I solve it if I have a constant coefficient, not just arbitrary functions of the independent variable, but constant coefficient? Then I can say a lot more things. And we're going to what can I do about non-homogeneous equations? We have techniques to do over there. And if those techniques don't work, then we have what's called power series, where you say, suppose I assume that the solution can be represented by a power series. Can I find a coefficient of that power series? Laplace transform is a transform that takes and makes solving differential equations more or less an algebraic problem rather than a calculus problem with a table lookup to get our answers. So we'll discuss that. And then the system of linear first order ODE, which we just gave that second example for. So now in the first order ODE, we have a number of different ways that can come up. And we'll talk about that. The separable way, which is exactly what we had for our first example. And then in general, if it's a linear equation, as I have this structure, then we can also write out a method of solution. And the method of solution will really involve, can we integrate? And we'll see how that works. And then the thing called exact equations, which we'll also cover. So in the general theory of linear equation, what we're talking about is having a set of derivatives of nth order with multipliers in front of them that may be a function of the independent variable, and then equal to not 0, but some function of the independent variable. And how can we solve that? We can say some general things about it, and we can say something on how to solve homogeneous equations, and we can say a little more when the coefficients, the a sub n's, are not just functions of x, but real numbers. And then we can actually write out things. And that's what we did in that second example. We wrote out we wrote that. So we have a number of different things we have to consider there. We did a simple case up there. Anyway, so that'll be going to, and then non-homogeneous equation. How do we solve an equation where now we got the homogeneous part? How do we get the non-homogeneous part and attach the two together? We have a number of techniques to go over there. And there's this the guessing technique, if you will, make an educated guess, and then this technique of variation of parameters, which we will look over and do something called a round skin, which we had in Cal 3, will come up again. The power series method is another method of solving differential equations. It can be a powerful one, but when those other ones don't work. And again, in differential equations, it'll be quite often there'll be things that don't quite work. So for some d, we say let's assume a solution that's of this form, a power series, and then ask what are the CNs that make it up. So we substitute into ODE and then solve for the CN, which can be a messy problem, but it's a way to go. It's a way to go when you don't have other things working for you. Laplace transform is another one, another technique. So it has an integral transform that has some very valuable properties in solving differential equations. Literally can make solving a differential equation, at least a linear ODE, to algebraic manipulations only, rather than integration and those kind of operation. And it can effectively deal with where we have piecewise continuous functions, and that typically can happen. And it can also deal with equation that not only has differentials in it, but integrals in it as well. And in the case of system of first order differential, we want to come up with procedures to solve that. And again, like I said, we use that in our second example, and we'll be talking about that. And then if it's, so we can write out the thing, if all the eigenvalues are real and distinct, which is exactly what we had in that second example, then we can definitively write out the solution. In our case, it was only 2 eigenvalues and 2 eigenvectors, but you in general can have n of them, and they could be also complex numbers. Anyway, so that's kind of an overview of where this class is going, and again, the main impetus of this review is to show that we need it to solve some very important problems, because we end up with this situation where we have a differential equation. We can describe the differential equation of what's going on in a particular phenomena, and then we want to find the functional relationship of that quantity or quantities that we're looking for. Anyway, hopefully you find this of some help. Thank you very much.